Desk of Ladyada.
Howdy everyone, and welcome to another Desk of Ladyada. It is Sunday. Fall is nipping at our heels. It was a little rainy and cloudy here in New York, so we actually stayed in and did a bunch of engineering. Woohoo! So it's time for the Desk of Ladyada.
Yeah.
So we can check what I'm up to. I did a whole bunch of stuff and I got a lot of samples in, but I thought maybe we'd start with the samples.
Let's jump right in.
Okay, so a couple weeks ago, let's go to the overhead. A couple weeks ago, we showed off the design for this infrared emitter that you can, plug in a JST-PH 2-pin cable into, and it would, it'll turn on and be very bright infrared emitter. And then we sourced the IR LEDs. Well, the final PCBs are now fabbed, and thanks to Penguin. Let's see if I can get this to focus a little better. Okay. Thanks to Penguin, it's got a beautiful silk screen with Futura Heavy. You can see the two infrared LEDs. And then I added a spot for an optional 5mm LED if you want to solder one in. Like if you were like, okay, I want a third LED because I want like full 360-degree infraredness. And I also did the tester today, and I was actually kind of experimenting. It's like I like to show when things don't work out, because like there's a lot of times I do stuff and I'm like, hey, I had this brilliant idea, and then it's like, no, it turns out not so brilliant, not so idea. But we make these Pogo Pin testers, and we have to solder in these Pogo Pins. The P75s are kind of my favorite. The crown or spear tip Pogo Pins. The thing that's really annoying about these though is like you solder in each one, and they like I like to give a little bit of give on the hole. Also, like when you get holes drilled in your PCB for pads, like you'd say 39 mils or whatever, but there's a little bit of variance. Also, sometimes they expand them or contract them, and so even though the Pogo Pins fit fairly tightly, they do tilt a little bit, and so like we have to spend a bit of time getting them nicely centered, which is annoying. So I was like, maybe I could use these Pogo Pin strips that we got in the shop. They come in strips of 9, and I thought, okay, I could cut them down. Maybe I'll show. Maybe we can go to the computer real fast, and I'll just show it in the shop. So
yeah.
What I'm talking about. Pogo Pins. These are the normal Pogo Pins, and then we had these like kind of Pogo Pin headers. And we put these in recently, and I was like, maybe like this could be a good alternative, because, oftentimes I have to measure or connect to like a strip that is on a feather header, and it's like, 12 or 16 pins in a row. And so it's like, well, maybe these will be ready to go. Like they come in a plastic strip already, so they're pre-aligned. And they're on a 0.1 inch boundary. But then what I didn't realize is I forgot to think, the Pogo Pin ends are less than they're not wider than the holes that we use. So if you go to go back to the computer, sorry, back to the overhead. I designed this so it's like, okay, you've got these holes here that kind of help you align, but these actually go straight through the holes in the PCB, which if you hold it down, it's fine. So I've got this tester here. If I plug it in, it does work, but it's not. It doesn't have that nice feeling if the Pogo pushes up against the PCB rather than going through the hole. It's kind of a better feel. So this would be good for something that didn't have any through holes to test. Only had test pads, but we tend to use a lot. Another thing is you can see it's flickering because the connection isn't so good. If you hold it down and you can see the IR emitting and detecting, it does work. It's okay. What I might do is when I'm like quickly putting together a tester, maybe I'll do this for like the first one, but I think it's not a long-term solution. So I might try to find some Pogo Pins on strips that have like a crown head, although I'm not convinced I'll be able to find one. So this experiment I tried it. So that's the IR emitter. Also put together some prototypes. So, we've got these little boards that we use for making a little power supply. So this is a TLV62569. It's a 3.3 volt 1 amp buck converter. But if some people remember, a couple of weeks ago we talked on the show about replacing the fan 5333 boost converter that I use for biasing OLEDs. Sometimes I just need like a high voltage, like a 12 volt or something reference, not like high current, maybe like 10, 20 milliamps. So we got this PCB with the TPS61040, which is one of the options we found. I don't think you can get any closer, but it's 2 to 6 volts in. For this board, I just set it to be 12 volts output. I don't quite get 100 milliamps. So that was kind of my guess. I was like, well, we'll see what I get. It turns out it's actually kind of limited. 3 volts, I can get 12 volts at like 40 milliamps. 5 volts in, I can get 12 volts at 80 milliamps out. So good for like a LED strand or maybe like a very small device biasing audio. If you need plus 12 volts for an op amp rail that's not rail to rail, you want to get a high reference voltage with some current. So I tested on the electronic load that I've got, which I always recommend. Electronic loads, before I bought them, I'm like, it's kind of ridiculous to spend like a couple $100 on this thing that's just like a big resistor. But it actually is really, really nice to have a digital load when you're like, I really want to just test a power supply. You've got your bench supply giving you your current in, and the load, you can dial it in, any milliamps, and tweak the knob while you watch on your scope to see the power supply stability. So I got this like B&K one, the B&K Precision. It's the 150 watt. It looks like the 8540 power supply. So I do recommend it. And then I did another Stemma board. I thought I showed this last week, but maybe I didn't. Maybe I showed it only on the Ask Engineer. So this, just a little prototype. Also, similar idea behind the IR LED. Which I just dropped. You have a JST PH in, so you can easily connect it to, wearables or a microbit or a circuit playground, or you can plug it into a breadboard, but it's freestanding. And this is a little motor driver with a 3 or 4 amp N channel FET, flyback, diode protection, LED indicator. So maybe I'll quickly just plug this in to test it out, show it off. So 3 to 5 volts input. So let me see. Get this, back it up a little bit. This is 5 volts, and then this is ground. So this is just a common thing, we're often like, somebody has a project like, I just want to like turn on a motor or a solenoid. I'm like, you gotta like wire up your ULN 2803, and it's kind of a pain. So this is, to make it a little easier. You see the LED tells you, this red LED tells you that it's powered, and then it just turns on whatever it is, up to 3 amps. So good for, anytime you want a PWM or just control a motor, solenoid, something that you just need that transistor and flyback, and maybe you want a couple LEDs to indicate. So
for the MOSFET, is it 3 volt or 5 volt output?
You can do 3. It's actually up to 12 volts, to be honest. It's the signal can be low. The power can actually be as high as, I think, 20. I think I use the DMG3415, which might be I think VGS can be 12 volts, I think. Maybe 6 to 12 volts, and then so the control signal can be that high, and then the power, I think, is 30 volts or something. It's up to 3 amps. Very low RDS on, so you're pretty much free to do whatever. Okay, so now to the meat of the matter. How am I doing on time? Okay, I'll go very fast. So I showed like this little tester, which we call a drop and beep tester, because you drop the board on and it beeps. And it takes it's less than a second. And a lot of I2C sensors are like that. You'd be surprised. You drop a BME 280, you can initialize it, do an initial reading, verify the voltages in 2 to 3 seconds. It's very, very fast. And so there's a little indicator LED and a beeper. And so people just test very quickly, beep, 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 beep. They can go through an entire panel almost instantly, and that's great. When I'm doing more advanced boards, like let's say let's see what I got here. This is, I think, a Feather. I got a Feather M4, which I don't know if I'll ever make again because I can't get these chips. But let's say I could. So to program these, historically I used a Raspberry Pi. So I'd have like, Raspberry Pi computer here. And I would use a OpenOCD or J-Link, and I'd program it using Linux to run the commands to do the SWD programming of the chip, and then I would test the USB enumeration. And that was fine, except the issue is that, Raspberry Pis, like, they're just not, they're fine as testers, but they're just not as, they're not super fast. Like, there is a lot of operating system stuff that has to happen. I mean, with the Pi 4, it probably wouldn't be as bad, but when I was first doing this on the Pi 1, it did take, a minute or two to kind of like get OpenOCD running, and you have to launch it and send the commands. And, if I did bitbanging, it would be slower, but if I used a J-Link, it was like $600. So what we did is a couple years ago, Tak and I, who wrote TinyUSB, we ported the I think maybe K-Town did this too. We ported the SWD programming protocol to Arduino so we could use a board running Arduino to SWD program a chip. And we got the SAMD21 going, the SAMD51, NRF52, NRF51 we did actually very recently. And the RP2040 we can do with mass storage. But for SWD programming, basically I was making these trinket M0s. Like you can program an AVR chip with SPI very, very easily. And you don't need very complicated hardware. SWD is a little bit weirder, but as I was starting to get into SAMD21s, I was like, I can't have a Raspberry Pi computer for every time I program, because it's also very easy. Somebody knocks the Raspberry Pi and the USB cable comes a little loose, and then now you have to reboot or it gets corrupted. I wanted a very solid state solution. So we came up with this idea of using one board running Arduino very quickly to bitbang SWD to program these boards, and then connect over USB, and then just make sure that the USB enumerates, because if it does, it means basically you programmed everything correctly. And so that is how we came up with the Teensy Based Tester Brains idea. This is actually a fresh one. But basically you've got a TNC 3.6, and the reason I like the TNC 3.6 is because it has a USB host, which is important because, again, I have to USB enumerate. And it has an SD card slot, which is really nice because then the firmware I'm burning is on the SD card slot, so people can change out the SD card very easily. It's like, update the firmware, update the program, or the test, just change the SD card. They don't have to, the people running the testers don't need to know anything else. So that's all great and wonderful, and we've made like hundreds of these. But there's a problem, which is, there is no TNC 36s anymore right now. And it's not clear when we'll get more. And I kind of had a stash that like about a year and a half ago when this started happening, I was like, okay, like I'm going to, keep 100 for us so we can continue to make boards. The problem is that we're out. And the TNC shortage isn't quite over. And I was thinking, I could port the code to the TNC41. It would probably be okay. I did make a couple tweaks to how USB works to optimize for the way you do testing. But I also thought like this is a really good opportunity to maybe diverge, because even though maybe TNC41s are kind of available right now, I've just sort of learned my lesson, like not to depend on a dev board that I can't control, because it's like, if I can't get TNCs for a project, what's one thing, but if I can't run the Adafruit factory because I can't get a dev board, that's kind of a bad scene. So you got the TNC36, you got the USB host, you've got this one doesn't have the power transistors. There's a couple power transistors here to control some voltage outputs, reset button, and one 16x2 LCD. And this is actually all through hole put together. We just hand solder these whenever we need them, and so we've got like a big collection of these teensy brains. But as I mentioned, I wanted to design something different, so let's go to the computer. And this is the original, and like again, this worked wonderfully for years, and I would still be using it if I could get these boards, but I can't. So the thing that's important is, I have a bunch of standard test pins, I2C, VBAT, power out, vMeasure in, ground, target reset, SWDIO, target, SWD clock, target, number 28, which is kind of like an analog input / extra GPIO whenever needed, UART, and a 3-volt power line. And so over the weekend, I kind of designed a totally new board. And one of the things I asked TAC to do is there was a Japanese person or some person who spoke Japanese who wrote PIO code for the RP2040 to do USB host. And it's not amazing USB host, but it's good enough to do like CDC and HID, it seems, and bit enumeration, right? Which is, again, if the board enumerates, I consider the USB working. I don't need to like actually transfer data on the channels. If it shows up and I get the right VID, PID, I'm like, great, the USB connector works, the USB pass-through resistors, the crystal, everything. You have to get a lot of things working right in order to enumerate USB and identify the VID, PID correctly. So the RP2040 doesn't have as good of a USB host stack as the Teensy TC36, but if I can move 50 to 75% of my boards over to this, then I can scrounge the Teensy TC36s for when I need them. So this is a cowbell. Another thing is, as I was doing this board, I was like, you know what? I'm a little tired of us hand soldering these. What if I make it surface mount, and then we can just do it on a 50 whenever we need a batch of boards? Because each product that we uses this tester brains, I need like 3 testers, like 3, because we often have 3 people testing at once, or we have backups. So I thought, instead of hand soldering these, which also sometimes there's a loose solder joints, let's put it through the pick and place machine. So this is Raspberry Pi cowbell connector. So you put your Raspberry Pi Pico RP20 here, and it's just very low cost, available, and there's like people have made versions. So even if the original Pico isn't available, there's others. If I have to do some Wi-Fi tests, of course, you can use the Pico W. It doesn't have the SD card built in, so I attached a micro SD card here. There's a lot of pins, so this is not a big deal. And then I connected a USB Type A jack to 2 pins, and TAC checked it out and said, yeah, as long as the D plus and D minus just have to be next to each other, you can use any pins. And then down here, I've got the LCDs. This is the large LCD. On the original, and I use a surface mount connector for that. On the original tester, we have so many pins, and again, the SD cards are built in, that I didn't have to like try to do some pin saving tricks. But on this board, the RGB backlight actually didn't have enough pins for it, and so I actually put down a WS2811, a NeoPixel chip, which we stock, just the SOIC version, so I can NeoPixel control the RGB backlight. And then I actually also was like, well, sometimes I might want a TFT. I need more resolution. So the 1.9 inch TFTs that we use, kind of bar style, it's a color TFT. I put down a connector, so you can use either. You can use either the TFT or you can use the LCD. I think the LCD is more legible. It's simple, but sometimes it's like maybe we need to show more data than 2 lines of text. So that's an option. Reset button. This is the power control for turning on and off the USB 5 volts, and then the VBAT pin. This is my little, like, I always mess up the RX and TX, these lines here going into the microcontroller board that I'm testing. I always mix them up. So I just put a switch here, and I just, it's like if I get it wrong, instead of having to redo the tester, I'll just flip the switch the other way, and it'll swap the 2, the RX and TX pins. So it'll always be right one way or the other. 1 through hole piezo. Piezos can't be surface mounted. They are done by hand. And then TAC was like, oh, put a SWQT connector on there on the I2C lines. You never know. Maybe some other sensor or device would be handy to have controlled here. So I had a little spot, and I added it. So this was just me, like, kind of messing around. I also put in a 18-pin FPC cable that has all of these test lines. I think for now, I do like to have big chunky wires going between the tester brains and the tester board, the device under test. But there could be some future where we use a small flex cable instead, just to so it's less likely people twist wires or anything, or they come loose.
Would you ever consider making the RP2040 tester a stocked item? Would love a TFT USB-A breakout and extras.
I don't actually think so. I don't mind publishing the files, but I don't think I would fabricate and sell this because
who would test the testers?
It's first off, it's hard to test the tester because we don't test the
tester. Then we'd have to test the tester before we could test the tester.
I know. And second, it's a very specialized piece of hardware that's just for me. I don't want to have to deal with if I revise it, I have to tell people, and then there's some guarantee of support. So I'll probably publish this. Online, but I think if I was going to make a board for like USB host, it would be I'd make like a Pi cowbell or something rather than this kind of monstrosity, which also might have mistakes in it.
Okay.
So anyways, this is the tester. So I just, I kind of routed it over the weekend. I think I have some really good improvements. I use every single pin. I love the RxTX flipper because it's so embarrassing. I love that I added a STEMMA QT, SD card, and the TFT option instead of the LCD for some situations. I think is going to come in very handy. And then we have to port, the Arduino code, make sure that the library for the SWD programming still works on the RP2040. I think it will. But the RP2040 is very fast. The reason I went with a Teensy TC36 is, of course, it's incredibly fast. And bitbanging, SWD, you can bitbang really fast to program a chip. And it actually makes a difference. Like if you are bitbanging at like 10 megahertz versus 100 kilohertz, it's going to make a big difference when you're transferring. You do the chip erase cycle, sure, but then when you actually have to blast that firmware over, especially if you have to do a read back, right? Because you not only have to write the firmware, but you have to read the firmware back. That's where I think the speed of the RP2040, and maybe we can PIOify the SWD because it is, again, this is weird bitbang. It's not a classic interface. It's a clock with one I/O pin that's bidirectional. It's an axle unusual.
Okay, the request, an additional one is Pi cowbell USB host.
Okay, fine. Yes, maybe we'll do that. Okay, so that's what I've been working on. So that leads us into the great search.
Here we go.
Where in the world is that part I need? The great search with DigiKey.
The Great Search brought to you by DigiKey, and for this time of the week, every single week, one Ladyada uses their power of engineering to show you how to find things on digikey.com. Ladyada, what is the Great Search of the week this week?
This week, I'm looking for a surface mount USB connector for this tester that I've designed. So let's go to the computer and I'll show the part in question. So the original board that I'm revising had all through-hole parts, which was great and everything. But these had to be assembled by hand, and I don't want to do that. I want to make 50 of these. Once I get the test design done, because we use these in so many boards, I want to just do a run of 50 and not have to hand solder them anymore. So this is like the classic through-hole USB-A connector, and it's great and everything, but for this new version, again, I really want it to be as SMT-ified as possible. And I did have like one, you can see this is an SMT USB-A. Not necessarily going to go with this connector. This is just the connector that was in my library because I'd used it before. So I put it down as a placeholder, but let's go and find some possible alternatives for the through-hole USB-A in surface mount on DigiKey. So let's go. Well, not translate. Go to DigiKey, not Digi. Okay, so let's go to USB Type A. That's the thin, long one. You're like, why don't you use USB-C? I don't actually know how to deal with the host side of USB-C. I just want to do USB-A because it's like I know it. I just want ground, D+, D-, and 5 volts. Okay, a lot of options. Connectors. Here you go. So I want USB connectors. It even has the photo of the USB-A connector. So I want connector assemblies. There's about 3,000. So let's take a look. Yeah, these look right. I mean, this is actually starting to look like these are just USB-As and all sorts of shapes and sizes is kind of a cool vertical USB-C, classic USB-B. All right, so let's start with, we only want the active products. Okay, and then we only want one port. So that's a really easy second filter. Next up, connector type, right? Like this is, all the connectors that are sort of similar, DVI and HDMI and Ethernet, whatever, they're all kind of in the same area. And there's micro B, micro A. I've actually used like micro A, but I really do want to have just that standard chunky classic type A connector. I don't need to save space. And moreover, I want it to be very user friendly because people are going to be using it. Might be like, what is this weird, like micro AB is like a very weird connector, to be honest. Okay, so I selected the A. There's a couple versions here, but I selected all three of them. I'll also pick up the dash. Okay, and then we're down to 600 components. Number of contacts. So, actually, no, we'll look at that later. Okay, plug or receptacle. We want receptacle because we're going to plug in a USB cable into this. Cool, let's see how we're doing. Okay, yeah, we still have some good options here. These are all looking about right. After I do a couple searches, I like to go down and just make sure, like, am I on track? Okay, so let's now do the mounting style because that's we want surface mount. So there's board edge, cutout, surface mount. Let's select those. We don't want free hanging or panel mount, and then surface mount, through hole. Now, a note: if you see through hole after surface mount, it's still mostly surface mount, but it might have a through hole board guide or tab or something. So it's okay as long as the surface mount comes at the beginning. So let's apply. Okay, now we've really cut it down to 85 bits. Okay, so the next thing is, some of these are USB 2 or 3, sorry, USB 3 or 4 or whatever. And so they'll have more contacts than the classic 4 contacts. I really want just 4 contacts. I don't want anything special. I don't want USB 3. So let's do that. And then that was also like a lot of they're in stock, so that's kind of good. So let's look at normally stocking. And let's exclude marketplace. So we get down to 45 options. Okay, cool. So next up, these actually look pretty good. So there's a couple things here that I noticed when I looked. So you see how this has like a little like a hooky thing. So even though this is surface mount, I feel like the pick and place is going to have a lot of trouble getting those springy bits to push through, because they push through and then they spring and hold up against the PCB. So this is surface mount, but I feel like it's hand assembled. I don't know. It might not have to be. Where something like this is definitely surface mount only. Like there's no through hole sections. There's also a few that have something like this, where if you see the plastic, this is literally going through the board, which I don't want. This is what was categorized as board edge cutout. The board itself has a rectangular slot. This means that you can have like the connector in line with the PCB, which is kind of, sometimes for enclosure design, it's actually quite nice. Because you have a clamshell with 2 halves cut out, and then, the USB goes in the middle and half is on each side. Honestly, I don't, for my uses, I don't want that. So I'm going to get rid of the board edge cutout options. And the next thing is I do want to pick and place this. So I'm going to go only with cut tape, digi-reel, and tape and reel. A bunch of these come on tray, and I'm not going to, it's like, no, I want this to go through the pick and place machine. So let's apply. Okay. So finally what I did is I actually, some of these were good. So this is actually kind of what I have already now. But I actually looked at quantity available, because this gave me a good idea of what was like a well-supported one. And so again, this is close to what I have on the board itself. The issue is that, there's a lot of leverage there. It's very easy. Somebody pulls on the PCB, they pull on the PCB or on the connector, and those USB type A connectors on cables are like amazing levers. They're like long and they're like extremely strong and they're molded. I feel like somebody just they would just yank the pads right off. This one's a little bit better. It has 2 sets of pads, so I feel like this would, if you really wanted to do surface mount only, this would probably survive better. Again, these are good, but I just don't know if the pick and place would be able to get this through to the PCB. So what I really liked was these Amphenol connectors, which were also very popular. And the reason I like these is they do have a through-hole tab, but the tab doesn't have like a massive kink in it. It's like, I feel like it'll push through, and you can even make the slots a little wider, so maybe there isn't anything in the way. But then you have paste on the pads, and it kind of solders it in place, sort of like how surface mount USB Type-C connectors work, right? It's pick and placed, and then you have these slots, and the slots, you have paste on top of them, and they just give a little bit of mechanical through connection to the PCB and gives it some strength. So I really liked this connector quite a bit. And what's interesting is if you look at the data sheet, they actually have 2 versions. They say, look, if you have a low-cost machining process, you can drill a hole. Look, if you can have a hole that's plated, but it's only good for like 1,500 cycles. But they're like, look, if you can get a slot, an actual slot, you'll have less leeway. This is good for up to 9,000 cycles, or if you use, I guess, this other part, 12,000 cycles. So I thought that was actually kind of interesting. They actually gave you 2 options for how to have footprint for this USB connector with different reliability. Either way, I don't, I'm happy with 1,500 cycles, or I'll do the slots, just for the heck of it. But I rather like this part. So this was my pick. And it's not too expensive either. It's, 75 cents, less than $1 in quantity, and comes on tape and reel.
That's a great search.
Where in the world is that part I need? The great search with DigiKey.
Okie dokie, here's a question. Is shield always counted as identical to the ground pin for the contact count?
No, that shielding is usually separate, and you don't necessarily want to connect it to ground. There have been a couple good app notes, which I can't recall off the top of my head, but with USB in particular, I do not ground the shield. And sometimes you would put a ferrite bead on the shield, perhaps, but I usually do not ground it. And that's, I think, pretty standard behavior. But I Google for like USB shield grounding to find out why. I think it gets grounded on the host side, not the device side.
All right. So you'd also want to search for 5 pins there.
Well, the USB-A connectors only have 4 pins. Because again, it's the contacts are the inside part of the USB, not the shielding.
Okay. All right, everybody. That's our show. We'll see you all throughout the week. We have a bunch of cool stuff planned and more. See you online. Thanks for spending your Sunday night with us.
Thanks,
that was
everybody.
The Desk of Ladyada.
Bye.